So here in chapter 3, we'll be talking about polynomial and rational function. The very first section is quadratic function and their graph. Okay. In chapter 2, chapter 1, we talk about the linear function. Okay. So the linear function in general, we can write our linear function as, so our linear function is f of x equals to mx plus b. Here m, b, these are any real number. Okay, so if we have a function of this type, then these functions are linear. And whenever we plot a graph for a linear function, what kind of graph do we get for a linear function? The graph is a straight line. Okay. Now, in this section, we will have a quadratic function. Okay. And the quadratic function, they look like, so our f of x equals to ax squared plus bx plus c. Now here, okay, so we have this function ax squared plus bx plus c, a, b, c. They are any real number, but a, it can't be equals to 0. Okay, so we have a function f of x equals, just let me be more specific, 2 x squared negative 3x plus 4. So we have this function here, and this function, if we make a comparison of this function and a linear function, what differences do we find here? So let me take linear function. My linear function f of x is 9x minus 2. So this is the linear function. Now if we compare these two functions, what is the major difference here? What difference do we find here? We don't have the same terms, but what are we trying to find here? What is the very big difference between these two functions? The exponent, right? So exponent here for the linear function, the exponent of the input is 1, okay, or the degree is 1, and in this function the degree is 2. And if we have a function with a degree 2, that function is a quadratic function. Okay, so this f of x is our quadratic function, and this is our linear function. Now here it does tell us our a, it can't be equals to 0. So if we compare this function with our general function f of x equals to ax squared plus bx plus c. If we make a comparison between these two, what do we have for a? So what do we have for a? 2, right? Okay, a is 2. What do we have for b? Negative 3. And what do we have for c? 4, right? So a is the coefficient of square term. Okay, the coefficient of square term is a. The coefficient of x term is b, and the constant is c. Now, in this quadratic function, if our a is equals to 0, do we still have the quadratic function? So, if a is 0, we can write this as a 0 times x squared is 0 plus bx plus c. And 0 plus bx is bx plus c. Now, is this still a quadratic function? No, right? The degree is 1. This x has exponent 1. And this is our linear function. If the coefficient of your square term is 0, the function becomes linear. And that is the reason why we can't have a equals to 0. You can have any number in a quadratic function other than 0. Okay, if you choose your a to be 0, then you won't have quadratic. It will be a linear function. Okay, that is the reason why we can't have a or 0 here. But a, b, c, they can be any real number, and a can't be 0. A can be any real number other than 0. Okay, and the domain for this function, for every quadratic function, is all real numbers. Now, what does it mean? So what does it mean by the domain of quadratic function is all real numbers? Okay, all real number is from negative infinity to positive infinity. What does it mean by domain? The inputs is all real number. Okay, and what is the criteria to be an input, or what is the criteria to be a domain? Can any number be, so we have a function, and can any number be a domain for that function? Not quadratic, just forget about quadratic. You have a function, and how do we know whether a number is a domain for that function or not? How do we know that? The value of x, but how do we know that value of x is a domain or not? When? Okay, you substitute your input in the function, and what should we get at the end? We should get out what kind of output? It has to be always real output, okay? Excuse me. So if you choose your input, and if your every input gives a real number output, then those inputs are the domain, okay? And for quadratic function, if you have a quadratic function and you are asked to write down the domain, just it's always all real numbers, okay? It doesn't matter what number you choose, we always get a real output. Now here, excuse me, we have this function here, f of x equals to x square. Is this quadratic function or not? Is this quadratic function? Now let's make a comparison of this function with our general function. So if we compare with f of x equals ax square plus bx plus c, what do we have for a? 1. A is the coefficient of a square term. Our square, we have x square, okay? And the coefficient of this is x square. If it's nothing, we do have 1 there, right? So 1, A is 1. What is b? That's right. There is no x term, right? So it's 0. And what about constant? 0, right? And the reason is that we can write x square as a x square plus 0 times x plus 0. Do you all agree? We can write, right? So for A, we have 1. For B, we have 0. For C, we have 0. Okay? Now, let's graph this function. So to graph, we need an input, x, and our output is f of x. Let's make a table. And we know the shape of graph for the quadratic function. What is the shape of quadratic graph for a quadratic function? It's always, we had a quadratic function in our section 2.8. It's always parabola, okay? Now we will see this here. Okay. Now what input do you want to choose? We know the domain of quadratic function is all real number. So we can choose any real number, okay? So let me go ahead and choose the very famous number. What is that number?
0.
Okay, that's the easy. So if our input is 0, how do we find output? You substitute 0 for every x. So we have 0 square, which is 0. So 0, 0. So we have, let me choose 1. 1 is square, that is 1. So we have 1, 1. So let me choose negative 1. Negative 1 is square is positive 1. So we have negative 1, positive 1. Let me choose 2. 2 square is 4. So we have 2, 4. And let me choose negative 2. Should be enough. So negative 2 square is positive 4. And we have negative 2, 4 points. So we have these 4 points. Now let's plot these points, and we'll get a graph here. So this is 1, negative 1, 2, negative 2. This is, okay, we need, this is 2, 1, 3, 4. So we have 0, 0. Okay, then we have 1, 1. Then we have negative 1, 1, negative 1, 1. We have 2, 4, 2 and 4. And we have negative 2 and 4. Now let's connect all these points. We get a graph. Now we can extend this, since the domain is from negative infinity to positive infinity, we can extend this graph all the way to the left and all the way to the right. Okay, here domain is all real number. Okay, who can tell me about the range for this function? Okay, so when we are talking about range, we are looking what are the y values that this function have for all these inputs. See, we can't extend the graph below the x-axis. It means all negative number are not the range. So the graph touches x-axis. It means 0 and all the way to the positive infinity is the range. So the range is from 0 to positive infinity. We include 0. The reason is that graph touches x-axis, and on the x-axis y is 0. Okay, so from 0 to positive infinity is the range for this function. Okay, now so let me, okay, now from here we can write the interval where the function is increasing, right? Can you tell me the interval where the function or a graph is increasing? So increasing means graph is rising. So what part of graph is rising? Okay, now so here this portion of a graph is rising, right? So the interval is we are writing the x values. So here the x values is 0, and since we can extend all the way to the right, it means up to positive infinity. Okay, so 0 to infinity is the interval where the function is increasing. And what about the interval where the function is decreasing? What is the interval where the function is decreasing? Negative infinity to 0. So negative infinity to 0 is the interval where the function is decreasing. And when you write the interval, you are using the x values, okay? You are using the inputs, and it's always small number on the left and large number on the right. Okay, that's how we write the interval notation. Okay, does anyone have question here? Let me know if you have any question. Okay, now let's graph one more g of x function. Then the h of x, you will do this, okay, by yourself. Okay, now let's graph this function here. Now this g of x, can we use transformation here? So what is the basic function for this g of x function? Is, okay, let's do the transformation, okay, concept. Okay, so here let's write the basic function. Basic function is, since this is a quadratic function, basic function is always y equal to x square. Now how do we get negative x square from this basic function x square? What do we have to do? Okay, now what does that mean to the graph? What happens if you multiply function by -1 to the graph? There is a reflection across x-axis. It means you just, so let me draw a graph for the basic function. So the graph, we already know from this first example. So this is the graph for the basic function, and you just imagine that you have a mirror along the x-axis. Now the image that we see is this one. So this is the graph for g of x equals to negative x square. So there is a reflection across x-axis. If you multiply by negative number, then there is a reflection across x-axis. Okay, so you can use the transformation concept here. Okay, now for h of x, so what happens for h of x? So our h of x is 2x square, and what is the basic function for this? Basic function is y equal to x square, right? It's the same since it's a quadratic. Basic function is y equal to x square. Now how do we get 2x square from x square? What do we have to do? Multiply by 2. And what happens to the graph when we multiply a function by a number which is greater than 1? it is stretched vertically away from the x-axis. Okay, now okay, let's see how it looks like. Okay, let's try to be like more accurate. So let me make a table here and let's make a comparison. So we have the input x, output f of, okay, is h of x, and we have the point x, h of x. So if it's 0 is 0, 0, 0. If we choose 1, then we have 2, that's 1, 2. If we have negative 1, that's positive 2, negative 1, 2. If we have 2, that's 8, so 2, 8. And if we have negative 2, we get 8, negative 2, 8. So this is the table. Now here, so once we have the basic graph for a basic function, we can stretch vertically away from the x-axis, or you can use this table. Okay, so here, so you draw the graph for a basic function. This is your basic function. Okay, and if you multiply by a number greater than 1, it is stretched vertically away from the x-axis. So this is h of x, or you can use the table. Okay, so when you multiply a function by a number greater than 1, it is stretched vertically away from the x-axis. And what happens to the graph when we multiply by a number which is in between 0 and 1? So if we have a function and we multiply a function by a number which is greater than 0 and less than 1, then it compresses vertically towards the x-axis. Okay, your graph is compressed towards the x-axis if you multiply by a number which is in between 0 and 1. Okay, now whenever you are asked to graph, you can use the transformation concept, okay, or you can use the table, or you can, okay, so until it mentions, you can just use any method. Okay, so let's go to the next one here. Now, so here we have our quadratic function f of x equals to ax squared plus bx plus c. So this is the quadratic function. Okay, and we can rewrite this function. Now I will just tell you this in a specific example how we can. But right now, just we have this quadratic function ax squared plus bx plus c. This is the quadratic function, and we can rewrite same quadratic function in this form: f of x equals a times x minus h. H is any number here, okay, some number, h squared plus k. We can always write these two are the same. They are only in a different form, but they are a same function. They have a same graph. They are exactly same. The only difference is that they are in a different form. Like for example, so if we have x plus 2, so is x plus 2 square and x square plus 4x plus 4 same thing? What do you think? We have x plus 2 whole square and x square plus 4x plus 4. These two are the same, okay? Like if we expand, so this is x plus 2 times x plus 2. And if we use a FOIL, this is what we get. These two are the same thing, but only their form is different. Okay, that's what I'm trying to tell you here. These two are the same function. This function are exactly same function, but they are in a different form. Okay, now if we have this form, we have a quadratic function, and our quadratic function is in this form. Then this form is the standard form. Okay, this is the standard form. The graph, as we said earlier, is going to be a parabola. We already seen that. Okay, and this parabola, if we observe parabola, let's go back. Now here in every graph we can find a point. Okay, in every graph we can find a point here. So see, we have this point here, we have this point here, this point here, Okay, and next graph we had somewhere here, right? Okay, we have this point here. What is the common thing about these points? What can we say about these points? Like we have this point here. What can we say about this point here? In every parabola there is one point. What can we say about that point? Okay, it's not the origin, it's the vertex, because the graph can be like this. For example, our graph can be something like here, and we can always find the point here, this point here. So what is the common thing in this point? In like every graph we have that point. We call that vertex. Okay, now what can we find like in that point? Now this is the point. Okay, now this is the point where your graph changes its feature. Okay, like here, let's see. So we have this graph. So as we move from left to right, we have a graph decreasing, right? The function is decreasing. Now once your function is at this point, the graph changes its behavior and it starts increasing. And it happens in every parabola. Like let's go to the next one. So here, so we have the graph. As we move from left to right, the graph is decreasing and it changes its behavior and it's increasing. Similarly, we have here, okay, here, the graph is increasing, and from this point, the graph starts decreasing. So that is the point where the graph changes its behavior from increasing to decreasing or decreasing to increasing. And that we can call that as a turning point. And that turning point is called the vertex. We call it a vertex, okay? So whenever you talk about the parabola, we have always a vertex. And that is the point where the graph changes its behavior from increasing to decreasing or decreasing to increasing, okay? So this is the vertex. Now, once we have our quadratic function in this standard form, your h is the x coordinate of a vertex and k is the y coordinate. Vertex is just a point, okay? And point has a coordinate, x coordinate and a y coordinate. So once we are able to write our quadratic function in the standard form, our h is the x coordinate of a vertex and k is a y coordinate of a vertex. And hk combined is a point, and which is called the vertex, okay? Now, we have an example here. So in number A, use transformation to graph f. Now let's graph this function using transformation. It does mention here, use transformation. In this case, you can't use the table. Okay, we have to use the transformation. And the very first thing is that we need to find the basic function. Now what is the basic function for this one? What is the basic function? Since this is a quadratic function, it's always y equal to x squared, okay? So let's write down the basic function. Our basic function is y equal to x squared. This is our basic function. Now, from basic function, we have to get this function. Okay, we are allowed to add, multiply, subtract, replace. Okay, now what is the very first thing we will do here? What do we have to do to this basic function? We have this basic function. We have x squared, and we need to get negative 2 times x minus 1 squared plus 3. How can we get negative 2 times x minus 1 squared plus 3 from x squared? Okay. Now, if we compare, you just compare and we can find it very easily, okay? Now, if we compare our basic function with the given function, so we look for the missing thing. So here, we have negative 2 in front of square term, right? So let's give negative 2 here. And how can we give that? We have to multiply, right? So we have to multiply basic function by negative 2. So multiply our function by negative 2. So we have a basic function. We are starting from basic function. Now we want negative 2 in front of square term. That's why we multiplied by negative 2. And what happens to the graph when we multiply by negative 2? we have, now let's see. So let's draw the graph for the basic function. So this is our basic function. Now when you multiply your function by a negative number, what happens? There is a reflection across x-axis. It means this graph flips, and since we are multiplying by 2, it is vertically stretched. Okay, so you draw a little bit narrow parabola, okay, than the first one. Now this is the second step. So after multiplying by negative 2, our basic function become y equals to negative 2x square. Okay, now what we need next? So we need, so if now let's compare this with our function. Now let's see what we need here. So instead of x, what we need? We need x minus 1. And how do we get that? What do we have to do? We have to replace our substitute, right? So you replace your x by x minus 1. So replace x by x minus 1. Now what happens to the graph? When we replace x by x minus 1, what happens to the graph? It goes to the right by how many unit? By 1 unit. Okay, so keep a note of a vertex. Okay, so this is our vertex here. So our 1, so we have, let's say this is 1 here, and at point 1 it has to be your vertex. Okay, so your vertex has to be here. Okay, so the graph we're gonna get is this graph. Okay, so let me rewrite the, now my function become y equal to negative 2, and instead of x we're gonna have x minus 1 square. Now what we need next? So let's compare this function with this one. So what is missing? Positive 3, right? So how do we get positive 3? We have to add. So add positive 3. And if we add, our function becomes y equals to negative 2 x minus 1 square plus 3. Now it's not enough by writing the function. You have to change your graph. Now what happens to the graph? When we add a number to a function, it goes up by how many unit? 3. Okay, excuse me. So let's say this is 1, 2, 3. So make sure this is the vertex. So we are moving our vertex over here. And our final graph is, so this is the final graph for this function. Okay, and the function we have f of x. Okay, f of x. So when you are actually use the transformation, you should have at least this information. You have to write what you did, and you have to have a graph for your graph. Should not be like, it should not be precise, exactly correct. Okay, if you have a close enough, you will get the credit, but make sure you have to just mention every transformation. Or you can just write in one statement, like you start from the basic function y equal to x square, reflect across x-axis, move right by 1 unit and up by 3 unit. You can just write in one sentence as well. Okay, or you can just mention all these steps. Okay.
Do we need to like graph each time we make a change to? Or just
No. Make sure you have the graph for a basic function and the final graph. That should be enough. And one is statement. Or if you want to mention every step, you have to follow all these. Okay. Okay, now the next here in number B, we are asked to write what is the vertex. It means we are asked to write the coordinate of a point associated with this parabola. Okay, let me write down my function one more time. So our function, this is for number B, our function f of x is negative 2 times x minus 1 square plus 3. Now from the graph, I think you can guess what is the coordinate for this vertex. So what is the coordinate for this point? Can you guess it?
1, 2.
Do you all agree it's 1, 3? Okay, 1, 3. Now, if you don't have a graph, we can compare this function with our standard form. Our standard form is f of x equals a times x minus h square plus k. So this is the standard form. Let's compare. So what do we have for h? 1, right? What do we have for k? 3. And hk combined, hk is h is 1, k is 3, and this is the vertex. Okay, if you don't have a graph, you can always compare your function with a standard form. Okay, now it's not easy to write a standard form. Okay, it's easy, but it takes time here. Now let's do in next example. Here your function, this function is not in a standard form. This is in a general form. Your standard form should look like, okay, it's already given here. So standard form should be in this form. But our function is in a general form. So here we have to write the function in a standard form, then we make a comparison and we find what we have for h and what do we have for k. Okay, so our target is writing the given function in a standard form. So let's start from our given function. Okay, before this, do you have any question? The previous example or like anything that we covered today? Okay, so if so, let's go ahead and start writing in a standard form. So we have a function f of x equals x square negative 8x plus 4. So this is the function. Okay, now the very first step is we have to have coefficient 1 for a square term. Okay, and which is, we already have that, right? The coefficient of a square term is 1. That's the very first step. And the next here is that we will write this expression in a square form, in a square of a binomial, and that's the one that we did in our previous lecture as well. So we had a completing square. So we solve our quadratic equation using a completing square method, and that's what we're gonna do here. So we will make the coefficient of square term square 1. Okay, after that we're gonna take the coefficient of x. So what is the coefficient of x here? 8. You can ignore the sign. Okay, it's same as the completing the square. Okay, we are completing the square here. Take the coefficient of x, divide by 2, square it, and in this case we are adding and subtracting. This is not an equation. Okay, in completing the square we add on both sides of the equation, but this is not an equation. So what we do is that we take the coefficient of x, which is 8, we divide by 2, we get 4 square, and we add and subtract this number together. So we have x square negative 8x, we add 4 square, we subtract 4 square, and plus 4. That's what we have the remaining. Okay, now I have a question for you. So why we just keep writing equals to here? Or do we have to write equals to here? Or now what is the point of writing equals to here? What does it mean? Like when you okay, not like when we solving an, okay, now like if we go back here, not here, okay, but here. So after writing this, we like, what is the meaning of this here? There's nothing to do with the output here.
So basically just you're continuing to say that f of x is equal to this expression.
That's right. So we have this expression, and this expression is same as this expression. They has to be equal. Okay, we can double check that. Okay, it has to be equal. Now, if we simplify our second statement, so this 4 square and negative 4 square cancel, right? And we are left with 8x square minus 8x plus 4. So your every step has to be equals to each other, and that is the point of writing equals to. It means these things are the same expression. Okay. Now, so one more time, you take the coefficient of x, divide by 2, square it, and add and subtract same square term, okay, like here. So you add 4 square and you subtract 4 square, and this make our equation equivalent, this make our equation same, okay. Now here, now we write this expression in a square term. So we take x from here, you take 4 from here, and we take sign from the middle term, we have negative, and we write whole square. So we have negative 4 square, that is negative 16 plus 4. We have like term, so we have this is x minus 4 square, negative 16 plus 4, that is negative 12. So you take the x from first square term, 4 from last square term, and the sign from middle term. And you can't have negative 4 square, it has to be always positive. Okay? This square term has to be positive, and that is why I write the positive square term first and negative second. Okay? And the reason is that this expression x minus 4 square is same as x square minus 8x plus 4 square. If you expand x minus 4 square, you will get x square minus 8x plus 4 square. Okay, these two are same thing. Okay, now we have this function. Now this is in a standard form. Now let's compare this function with our standard quadratic function, and that is f of x equals a times, so we have x minus h square plus k. Now we want to know what is h and what is k, that is our vertex. Now if we compare, what do we have for a? 1, right? A is the coefficient of this parenthesis. If there is nothing, it's 1. Okay, for x we have x, for negative we have negative, for h what do we have? 4. Okay, our h is 4, so we have square. Now here, so we need to have a positive, but we have a negative here. So can we rewrite negative 12 as a positive times negative 12? Can we write? It's the same thing, right? Okay, now we have positive, and for k what do we have? Negative 12. So our vertex which is hk is, our h is 4 and k is negative 12. So this is the point where the parabola changes its behavior. Okay, it might change from decreasing to increasing or increasing to decreasing. Any question? So it's pretty similar to completing square. Okay, the one difference is that once you take the coefficient of x, divide and square, you have to add that square term and subtract. But when we are solving completing square method, we add that square term on both sides because it was equation, but this is not equation. So we add and subtract. Okay. Okay. Now, so let me draw. So we already have a graph for this. Oh no, we don't have a graph for this function. Now I think we can draw the graph for this function very easily. So we have, okay. So let me draw a graph, and let me take a very general graph. Okay, I'll just take a graph for a basic function, and we will study the different feature of a basic function. So we have this parabola. Okay, and we already know what do we call to this point? What do we call to this point? We call vertex. It is hk. Okay. Now, can you just tell me the interval where the graph is increasing? So this is your hk, okay, in general. Okay, in this case this is a 0 0, but let's write in a general. So like as we are moving from left to right, so we are moving from left to right, so graph is falling down up to Okay, it's 0 0. So let me make a slight change here. So I don't want it to be 0 0. So let me make it, okay, let me make my y-axis is over here, so you won't have a confusion. Okay, I know it's easy for me to make a change, but it may not be easy for you. Okay, now this is the graph I have here. Now what can we say about the interval where the function is increasing? What is the interval? From negative infinity to this point. What is this point here? The coordinate of this point is hk, so this is h, right? Do you all agree? So from negative infinity to h is the interval where the function is increasing. Oh, sorry, that's right, it's a decreasing. Okay, so let me erase this interval. So the decreasing interval is from negative infinity to h. Okay, now as we move from this vertex all the way to the up, our function is going up. It's a interval where the function is increasing. So from h, so we are taking x values, okay, x coordinate to all the way positive infinity. Okay, now so here let me draw a vertical line that passes through a vertex. So I have this vertical line that passes through a vertex, and this vertical line is parallel to our y-axis. Okay, and what it does, this vertical line divides our parabola exactly into two parts, similar parts. Okay, and this vertical line is called the axis of symmetry. Okay, so here this vertical line that passes through vertex, okay, is the axis of symmetry. So this is axis of symmetry. Axis of symmetry is a line, okay, it's not a point. Vertex is a point, but axis of symmetry, it is a vertical line that always passes through a vertex. Now axis of symmetry is a vertical line. If that is a line, how do we represent a line? How do we write a line? Using a, one way is to draw a graph. Now what is the other way to write a line? How do we write a line? Using a linear function or an equation, right? So we use equation to write the axis of symmetry. Now this is a vertical line, and there is a specific way to write the vertical line. So what is the equation of a vertical line looks like? So for every vertical line, the equation is x equals to, what would be in this case? X equals to x intercept. Okay, so we are writing the equation for this vertical line. Okay, so for this vertical line, what is the x intercept? And we know this point is h. X intercept means it's a point where a line crosses x-axis. So at what point the line crosses x-axis? At h. So x equals to h is the axis of symmetry. So make sure whenever you are writing the axis of symmetry, it has to be in equation form. You must have x equals to and h. H is the x coordinate of a vertex. Okay, so it's an equation. When we have the vertex, we are writing a point, but when we have the axis of symmetry, we are writing the equation. Okay, okay, the next thing, now let me write function one more time. Quadratic function f of x equals to ax squared plus bx plus c. Now if your quadratic, if the coefficient of square term a, okay, if the coefficient of square term a is greater than 0, you have a quadratic function and the coefficient of square term is greater than 0, then our parabola looks like this. It means the parabola opens up. If the coefficient of square term is positive, the parabola opens up. Okay, if the coefficient of square term a is less than 0, the parabola opens down. So you have a quadratic function, you look at the coefficient of square term. If the coefficient of square term is positive, it's a number greater than 0, then the parabola opens up, and you have the quadratic function with a coefficient of square term less than 0, negative in front of square term, then the parabola opens down. And that's what we can see in our examples. So if we go back to our examples in the graphing here, we had a graph. Okay, now here this function has a negative coefficient, right? And because of that, our final graph, it opens down here. So the final graph, see, the parabola opens down. Okay, and similarly, so here our coefficient is positive, so parabola opens up. So here opens up. So we have the coefficient negative, so our final graph opens down. So the coefficient of square term, it helps us whether the parabola opens down or up. If it's positive, it opens up. If it's negative, it opens down. Okay. Okay. So here, one more thing. So this parabola has like infinite number of points. So what can we say about the height of this point? So we have this point, which is the vertex. What can we say about the height of this point in comparison to the height of other points? That's the lowest point, right? So if the parabola opens up, then we get the lowest point. Okay, if the parabola opens down, so if the parabola opens down, like for example, if we have a graph that looks like this, the same vertex will be the at highest point, right? So we'll use this concept to find the maxima and minima in our next section. Okay, so for today, let's do this much, and remaining we will do tomorrow.